now look at sampling distributions and what's known as the law of large numbers. But to start with, we're going to define two things. The first thing we're going to define is a parameter. A parameter is a number that describes a population. And two examples would be mu and sigma. Mu for the population mean and sigma for the population standard deviation. On the other side of that, we have a statistic. And a statistic is a number that is computed from sample data rather than the entire population. Examples of this would be x bar for the mean of a sample and s for the standard deviation of a sample. So the idea of what we want to look at is we want to see how these statistics are related to our parameters, how things from the sample can actually, what they can tell us about things about the population. And this is the idea of statistical inference. The idea is we want to use our sample data to draw conclusions about the entire population. So how do we do that? Let's suppose we have the sample mean, x bar. We know this is not the exact as the population mean. It's very rarely exactly right, and it's going to vary from sample to sample. If I have a different sample, it's going to be slightly different. However, this is an actual reasonable estimate for the population mean. So even if we know that the sample mean is not exactly right, why is this a good estimate for our mean mu? Well, the idea is if we just take our sample to be larger and larger and larger and larger, then this sample mean x bar is guaranteed to get closer and closer and closer to mu. So let's look at a specific example to explain this a little better. We know that the mean result of rolling a die is 3.5. This is something I actually calculated when I showed you how to find the mean from a probability distribution. So this would be my mu value. We know this is the population mean. Now I actually rolled a die 3 times. I got 3 different numbers, and when I averaged them, their average was 4.67. So that would be my sample mean. So 3.5 is my parameter, 4.67 is my statistic. And we can see these are not close at all. This time I rolled my die 50 times, took all of the outcomes from those 50 rolls and averaged them. And this time I get 3.12. That's still not exactly 3.5, but it's a lot closer than that 4.67 was. This time I rolled my die 500 times, averaged all the results, and got 3.546. And we can see now we're getting really, really, really close to 3.5. And this is what I meant before. And this is known as the law of large numbers. The bigger our sample is, the more and more times that we do our experiment, the closer and closer and closer we're going to be to the true parameter. The more times I roll the die, the closer and closer I will be to the true 3.5. So what about small samples? It can be a lot harder because, like I just said, the law of large numbers says we need bigger and bigger and bigger samples. What if I can't do that? So my question, what about estimating my population mean by my sample mean, estimating my parameter by my statistic from a sample of size 10? Well, we're going to use the idea of a sampling distribution. So what exactly does that mean? In order to make a sampling distribution, our first step is going to be to take a large number of samples of size 10. So instead of just one sample, we want a lot of samples, all of the same size. We then want to calculate the sample mean x bar for each sample. So we actually want to find the mean of each sample. We then want to make a histogram from the values of these sample means. We then want to determine the shape, center, and variability. So let's look at an actual example of building a sampling distribution. We'll determine the shape, and then we'll talk about center and variability in a separate video. Let's suppose I have a very small class that only consists of 4 students. I gave these students a quiz, and their grades were a 2, 6, 4, and 8 out of a total of 8 points. And I'm going to look at samples of size 2. So the first step in a sampling distribution said to take a lot of samples of the same size. I'm actually going to look at every single possible sample of size 2 with replacement. So here are all the possible samples of size 2. We can get 2, 2, 2, 4, 2, 6, 2, 8, etc. The second step was then to find the mean of each of these. So now I have all of the means of each of these samples. The next thing we want to do is build a histogram. We can go back and look at our table and see that there is one sample that has a mean of 2. There are 2 samples that have a mean of 3, 3 samples that have a mean of 4, 4 samples that have a mean of 5, 3 samples that have a mean of 6, 2 samples that have a mean of 7, and finally 1 sample that has a mean of 8. So we then wanted to talk about the shape, and we can see that this is actually normal. We can even say here that the center is 5. I won't quite go into the variability here now, but the next question should be, is there anything unique about this, or is this always going to happen? Should we expect a different shape every time, or will it always be the same? What about the center, and what about the variability? And this is what we'll look at in the next video with the central limit theorem.